So here is a proposition in that. Okay. So now we are just, in this lecture we are always working with graded case. So R is a polynomial ring, maybe set up the notation. R is a polynomial ring, graded, and degree of xn equals 1, and I inside our ideal, homogeneous ideal. Okay, proposition. Let this greater than be a monomial order. Then the Hilbert series of R mod I is the Hilbert series of R mod the initial ideal of I. Okay. We can't talk about Hilbert series if it were not graded. The initial ideal is always graded. It's an ideal generated by monomial, so it's always graded. But if I is not homogeneous, the left side is not a meaningful object. Okay. So in particular, dimension of R mod I is dimension of R mod in I. So any quantity that can be recovered from the Hilbert series should agree for both. So this one is the dimension which is given by the exponent in the denominator, 1 minus t to the something. So that determines the dimension. So dimensions are the same. Multiplicities are the same. Okay. And because of this, height is the same. So, sorry, this in is always with respect to the given, and the proof is the same, which is, okay, if we take in f inside I, f not 0, this set, the complement of it, sorry, not in R, sorry, not the set of monomials of R not in this set, in f inside R, f inside I, f non-zero, okay, is a basis of R mod I, is a k basis for R mod I, and for the same reason, and of R mod in I. Okay, it has a okay. So this is, I mean, remember they are not the same elements. The monomials modulo I in this case and monomials modulo in I in this case, but it's the same, I mean, there's a bijective correspondence. So these both have the same dimension, but that's not the point. The point is that this respects the decomposition of R mod I as a R mod I in degree I direct sum and R mod in I as the decomposition. So this decomposition, remember, is as k modules. Okay. So you can break up the set of monomials in this list, monomials of R not in this set, by degree, and of that set in a fixed degree will be the basis for R mod I in that degree and also for R mod I in that degree. One should say gives, because it's a residue class modulo I. Okay. So therefore in each degree the dimensions are the same. So therefore rank of R mod I in degree I is same thing as rank of R mod I in degree R mod in I in degree I, and this multiply this by t to the I and then take the sum, you will get the same function on both sides. So the Hilbert series are the same. Okay, and dimension, so dimension is given by, remember Hilbert series of M is given by some Qm of t over 1 minus t to the dimension n minus 1. Okay, so if two modules are the same Hilbert function, they will have the same dimension and the same Qm, and multiplicity is Qm of 1. Multiplicity of M is Qm of 1. Okay. So therefore, things that depend, if two modules are the same Hilbert function, they have the same dimension and same multiplicity. What about height? So this is from the previous lectures. Height of I is dimension of R minus dimension of R mod I. This is true not in arbitrary Noetherian rings. It is true in a polynomial ring, which we didn't completely prove it. We needed a stronger version of Noether normalization, and we needed a going down theorem to prove the statement, or to prove a statement which would imply this. Okay, so therefore, but if dimensions are the same, this is this is by the observation, this is by the theorem which we only sketched and not proved, and the same thing here. Okay, I and in I have the same height. Okay, let's do a quick example to use this idea, and we will come back to this example about computing what is called Ccgs and being able to compute them. Okay, so R is a polynomial ring in 3 variables. Okay, and let's say we are considering graded lengths. Okay, so let f1 be xz minus y squared. The leading term is this. f2 is xz, let's call this thing f2, otherwise f1 is xy minus z squared, and in graded lex this is a leading term. So the leading terms do have some common factor. So let's cancel that thing. So let's take f3 as z times f1 minus y times f2. Okay, and this is z times f1. Z times f1 will give a z cube, and y times f2 will give will give a y cube, and this is y cube minus z squared. Okay, and its leading term is this. Okay, so if you just took the, we have seen this, if you just took the leading terms of the generators, that may not give all the initial terms. Okay, a minimal generating set need not be a Grobner basis. Okay. So now we want to claim that the initial ideal of I is generated by these 3 things: xy, xz, and y cube. There is nothing else. So we will use ideas of the previous result to prove this. Okay. So we'll check this by looking at Grobner basis. So let's put degrees here. Okay. Let's put R mod I and then let's put R mod in I. Not R mod in I, but R mod this ideal. This is the claim. xy, xz, y cube. So we know this statement, right? It's the other direction that we want to prove. Okay. So here in degree 0, R mod I is just, basis is just 1. So I'll write down the basis, okay, and the Hilbert function. Similarly, basis is just 1 and Hilbert function is just 1. In degree 1, we have only killed a higher degree polynomial. So here it is just x, y and z, 3, x, y and z, 3. In degree 2, so what is left over? So these are this is what we went modulo by. Each time we see, so degree 2 is quadratic monomials. Each time we see a y square modulo f2, we can write it as xz, and similarly each time we see a z square modulo the ideal, we can write, so sorry, I didn't clarify what I is. I is the ideal generated by f1 and f2. Okay, so modulo I, z square, y square can be written as xz and z square can be written as xy. Okay, so now therefore there is x squared, then there is xy, xz, and y square can be written as one of these, z square can be written as one of these, yz cannot be written as one of these. So that's actually independent. Okay, and then we can check what is in degree 2, what are the monomials not in this, not divisible by that. So that is also x squared, y squared, z squared and yz, 4. So both Hilbert functions are 4. Okay. So I'll just do one more degree and then we'll see that it is actually 1, 3, 4, 4, 4, 4 and similarly 1, 3, 4, 4, 4, 4. Okay. So in degree 3 we have x cube, when we have x squared y, these are leftover things, x squared y. Each time we see, so x square y, x square z. If you see xy squared, if you have xy squared, then using this it can be rewritten as x square z. So we don't need to take xy squared. Same reason we don't need to take xz squared. I mean similar reason using this. Okay, and okay. So now let's look at things that are not divisible by x. So there is y cube, which can be written in terms of this xyz. Okay, and however xyz, x square z xz, xyz is new. I mean xyz cannot be written using these relations. It can be changed to some anything relations. So there is xyz. And this is all that there is. There is 4. And similarly, if you do this, there is 4. And then the conclusion is that the rank of R mod I in degree 2 onwards, I is equal to 4 for all I greater than or equal to 2. Rank of R mod, the ideal generated by these things, xy, xz, y cube in degree I is equal to the same rank as this for all I. Okay. And this is equal to, by the theorem, this is equal to rank of the initial ideal of I for all I in N. Okay. Now, okay. But remember that this ideal is inside the initial ideal. Okay. So, but R mod x y x z y cube surjects onto R mod in I. What is the kernel? Well, because of this relation, kernel will have Hilbert functions constant 0. Okay. So let's just go back here. Because of this inequality here, so this thing here, this now implies that kernel is 0. Okay. If there is a kernel in some degree j, then this module will have more in degree j than this module. In degree j, this module will have bigger rank than this one, but that's not what the calculation shows. They are all the same thing. So therefore, the kernel is 0. Okay. So this is a way to use these ideas to say that we have already constructed the Hilbert initial ideal. Okay. So comparing Hilbert function. Okay. So now I want to introduce a new topic. This is going to be related to the next few lectures, which is the following, called Ccgs. Okay, so what is that? So we will only worry about homogeneous ideals now. It can be done in any. Okay. So let F1 through Fm be in R, same R, polynomial ring in n variables graded. Okay. Be homogeneous elements. Okay. We can do it in any case. I mean, more generally, for any Noetherian ring, etc. But let's. Okay. A Ccg of these things is an R linear relation. Okay. So for example, x and y in kxy has a Ccg y times x minus x times y equals 0. So this is maybe let me just use a different letter. So just to say what is f and what is r in this notation. So let's put the f's in green, okay, and so this x. So these things in red are the coefficients Ri, and these things in green are these f's, just to. Okay, so this is a Ccg of these two elements. Okay, so how would we find Ccgs? That's what we want. But what is the, okay, so observation. Let f be finitely generated, graded. We can even just say f be equal to some. So we are given this f1 through fn. Let di be the degree of fi, because we already assume that it's homogeneous. Then we have the following free module, r twisted by minus di, direct sum, mapping onto I, in which a basis element here of degree di maps to fi. So ei maps to fi, where ei is a basis element of degree di. So technically we should say choose a basis element with like this, give it degrees di as above, and then consider the free module. It is graded, this one, and then ei maps to fi. This is a surjective map. Okay. So where do Ccgs come? Okay. Then Ri fi is 0. That means that is we have a Ccg. if and only if the element Ri, Ei in that free module, so sorry, this basis is E1 through Em basis, degree of Ei is Di. Okay, so this is, okay, so this free module is in the kernel of the above map. Okay. So in some sense, asking for Ccgs is same thing as asking for kernel of this map. Okay. And okay. So then if you have algorithms to find kernels of group module homomorphisms, then we can find all Ccgs. Okay. So this is what we will okay, and building this up into what is called a free resolution is what we will be doing in the next few lectures. But before that, I want to show an example which tells us that if we know to compute Grobner basis, then we can compute Ccgs. So we'll do it for an ideal now. Later, I will mention that it can also be done for modules without explaining how it is done. And that is how we will start, free resolution can be constructed. So these things will be explained in the next few lectures. So right now, let's just look at how to use the same calculation as we do in the Grobner basis to come up with Ccgs. So we will just do this in Macaulay. Okay, so here it is the same example from the last time. F1 is xz minus y squared and xy and xy, F2 is xy minus z squared, okay, in GLEX, and then we want to compute the S polynomial S F1 F2. Okay. So we use different convention from what we did in that example, but so the leading term is xz, leading term here is xy. So multiply this by y and this by x and then take by z and then take the difference. Okay. So S F1 F2, we call it F3. Okay, so this is minus y cube plus z square. When we did it earlier, we had swapped the order, so we got the negative of this. But let's keep this convention. Okay, so we look at this. So none of its terms are divisible by the initial terms of f1 and f2. So this is our reasoning is what's going on in Buchberger algorithm. So we'll keep it. There's nothing to simplify. Okay, no further division algorithm remainder to be taken. So we now have f1, f2, and f3. And we actually proved that this is a Grobner basis. Okay. But we don't know it. So we'll ask Sf1, F3. So Sf1, F3 is, so you have to multiply F1 by minus y cube and F2 by xz and then take the difference. So we got this one. Okay, so some term. Now if you look at this one's leading term is divisible by the initial term of F1, right, xz. So we try to simplify it. Okay, so what we did was we had to multiply by z cube. So OO plus z cube times f1. The plus was to cancel this minus sign. Okay, so we got y squared, y to the 5 minus y squared z cube, which is actually minus y square f3. Okay, and we just check OO plus y square f3 is 0. Okay, so this is indeed true. So what is the conclusion that we got? S F1 F2 plus, sorry, I forgot the subscripts here. It should be F subscript 1 and F subscript 3. S F1 F3 plus Z cube F1 plus Y cube plus Y square F3 equals 0. We can rewrite it to look at like this. But then it just says F1 F3 minus F1 F3 equals 0. Like that XY minus YX is 0. Okay, so in this case, it is sort of an obvious trivial Ccg, but let's check this is not always the case. Okay, so let's check F1. Yeah. Let's now compute SF2 F3. Okay, so we ask, this is the computation, we ask minus y square times F2. There is a common factor, so minus y square times F2 minus x times f3. Okay, so we get this polynomial. This polynomial, it is immediately clear that this is f1 times z square. So we just ask, I mean minus f1 times z square. So we just ask z1 times z square times f1 plus OO, and it says it is 0. Okay, so therefore, what the conclusion is that we got a Ccg. Now this is not one of those trivial Ccgs. z1 square f1 minus y1, sorry, z square f1 minus y square f2 minus xf3 equals 0. Okay. So the same procedure which gives the Grobner basis also, if you rewrite it nicely and just work through it, it gives us the relations among the generators. Okay. So this will be used for us to build what is called free resolution in the and try to learn, I mean, use that information in some context. Okay. So this is the end of this lecture. So the next few lectures would be devoted to preliminary understanding of free resolutions, some invariants coming about free resolution for homogeneous ideals, and how to use it.